Hi, and thank you for viewing this video abstract about the role of roles in COVID-19 transmission. Today I'm going to be talking about partitioning interactions to inform social distance relaxation and implementation in Minnesota. What do I mean when I say partitioning interactions? Well, you might imagine you interact with some people when you're at school, others when you're at work, and still others when you go to the grocery store. How can we use this knowledge of these different types of interactions and how they differ from one another in order to better inform our interventions and reduce disease spread? This was work conducted with a bunch of people in the DVM, mostly out of Megan Kraft's lab. And it really stemmed from a question of how can we relax this household isolation that we've been in for a month or two, for the last few months, and how can we relax it in a way that minimizes the rebound in transmission and consequent death? We know that when we increase the number of interactions that we will see an increase in disease, but are there ways to do it in a smarter way? And in addition to this reopening question, we were motivated by the observation that contact patterns and individuals themselves are heterogeneously distributed, both through space, for instance, in the urban-rural divide, and through time. For instance, you see more people during the day than you do at night. And how can we target interventions to these different types of interactions and these different individual statuses in order to get the most benefits at the least cost? Our framework involves constructing a network of interactions and combining that with an underlying disease model. And by putting these two things together, we can get an understanding of the dynamics that will allow us to better inform interventions moving forward. A network is constructed by two components. First, there are interactions between individuals. These interactions can be of different types. For instance, here we have a group of students that interact through classmate interactions, and here we have a group of people who work together. And of course, every individual is also a member of a household where they have these inter-household links that are read. Individuals can also vary in their susceptibility to the disease. Here we do a simple vulnerable, non-vulnerable binary, and we classify people into these two categories. Of course, there are many other types of interactions and perhaps more nuances to individual status than what we're mentioning here. For instance, you might go to a religious institution and see people there, or if you visit elderly people in a nursing home, that's another source of interaction. As the disease progresses, every node in the network passes through different stages according to this disease model. They start out as susceptible, and then they become exposed, infectious, and eventually they either recover or die, succumbing to the disease. What this looks like, empirically, is that we have a single individual that starts out infected, and then the disease quickly spreads through densely connected areas of the network. Some individuals, such as these sparsely connected individuals out here, manage to escape the disease unscathed. What gets more interesting is when we allow the network structure itself to change in the middle of the simulation. Here we start out with a number of individuals being in a state of household isolation. There's a small amount of disease persisting over this time, but as soon as we reopen society, allowing all the different forms of interactions, we see a spike in the disease presence. And by adjusting which types of interactions we allow to resume here, we can adjust the height of this peak in infections and thereby inform the most appropriate way to reopen society. If these kinds of questions are interesting to you, I encourage you to check out our Shiny app, which is online at this URL. And with that, I'll thank you and have a nice day.